Morning. Thanks for showing up, or it could be afternoon wherever you are. We're going to run through a few years worth of work with Bakken reservoir rocks and Bakken oil using the CO2, looking at mechanism for enhanced oil recovery and hopefully associated storage. My name is Steve Hawthorne. I'm from the University of North Dakota Energy and Environmental Research Center. Thank the folks that pay for this work. A lot of support has come from Nettle. We appreciate that. I'm going to talk about four different basic experiments here, just a little bit on multiple contact minimum miscibility studies. Also look, I think this is a little more complicated, at what the CO2 when you inject it onto a bulk oil, what it actually dissolves, what hydrocarbons are actually in that quote miscible phase. To extract some rocks, see whether we can get oil out of Bakken shales in the middle Bakken and Three Forks target zones, and some isotopes. So the studies we're doing here, the rock samples are all from the North Dakota Core Library, which we appreciate the support very much on that. All the experiments for middle Bakken, we took 110 degrees C or 230 as a typical temperature, 260 Fahrenheit for the Three Forks, typical temperature. These rock samples are not resaturated. This is oil that's there after they were collected. So they often have lost a lot of volatiles, and so we're extracting the hard compounds. But right now, this stuff was put there by nature, not by us. And the test oil that we're using most of the work here is API 41, typical light crude. First experiment, multiple contact minimum miscibility pressure. We use a vanishing interfacial tension technique, capillary rise technique, first pioneered by Rouse Group. We modified it some, got a patent on it. So we have three capillaries right here, standing up in a little rack. They're above 3 mils of oil in this, through this view cell. And you see they have three capillaries. Oil goes up in the capillary by natural sort of extension. When we put 870 psi of CO2 on top, the oil level drops in each capillary as it continues to drop until we approach MMP. Then the oil level in the capillary is near zero because the interfacial tension between the upper CO2 and the bulk oil phase is near zero. And finally, when we're above MMP, the hole up in the capillaries goes away. And this is a plot, typical plot you get from here. So we have the three capillaries. This is one run. It's about an hour experiment if you all are set up and tear down. Large capillary, medium capillary, and small capillary. You extrapolate those to zero capillary height, and that is your MMP. We've done a lot of these. This just shows the typical results for Three Forks produced oil and a middle Bakken produced oil. Duplicate experiments. These are two loads of sample, two duplicate experiments. The air bars here are the three capillaries in each case, and we have gotten good agreement with Slim tube comparisons. Okay, major thing here, 2,700, 2,500 typical MMPs for Bakken oils. Hydrocarbon compositions in the middle miscible phase. Here we're staring down the barrel of that same cell, high pressure view cell, and Dave Miller in my lab figured out how to put capillary sipping tubes. So here's the CO2 phase up here, here's the oil phase, percolate the CO2 through 10 mils of oil so it comes to equilibrium as it goes up into the cell. We maintain the pressure with the pump that's connected down here, so the CO2 is always there. We get no pressure drop here, and after letting it come to equilibrium, sips off a sample, collects it, and analyzes it by GC. Okay, these plots here on the left side are milligram per milligram of total crude oil dissolved per mil of CO2 at 1,500, 3,000, and 5,000 psi. The units on the left are milligram per mil. I'm sorry, these are milligram on the left and milligram per mil on the right, which is more like a scuff number, okay, on the CO2. Again, 1,500, 3,000, and 5,000 psi. To note here, regardless of which units we're using, 3,000 is well above the 2,500 MMP, yet when we continue to put more pressure on, more oil dissolves. MMP does not tell you what's going to dissolve. And if this is a dissolution mechanism, you need a good solvent to get these hydrocarbons out of the rock. Higher pressure is going to work better. It dissolves more oil, period, regardless of MMP. The other thing is CO2 is not a very good hydrocarbon solvent for higher molecular weight. Happily, very little of the crude oil in Bakken oil and Three Forks oil is high molecular weight. If you look at the amount of C20 to C36 dissolved by CO2, it's less than 1%, 1,500 psi. It's about 25% at 3,000 psi, and still is only 40% at 5,000 psi. So your residual oil will have higher viscosities and lower gravities because of heavy oils left over. We've observed that in both commercial and pilot scale EOR floods, even at ones that have been done at 2 times the pressure. So that's just the way it is. CO2. Okay, crude oil recovery from Bakken rock samples. Little lithology. I am an analytical chemist by training. My PhD is in environmental analytical chemistry, so excuse my terminology, so I'm showing the picture. Three Forks is one of the drilling zones at the bottom here. Lower Bakken Shale, one of the source shales, is an important sample. Middle Bakken, the 2-3 layers basically is a target zone. That's where most oil is produced, and then the Upper Bakken Shale here. I want to talk about pore throat size when we see about getting rocks, oil out of these rocks. If you look at what we have here, the median pore throat radii, is 12, 13, 14, whatever, nanometers for Middle Bakken, and only 2 or 3 or 4 nanometers for the shales, which is really, really small. How small is it? The C14 molecule, kind of your generic molecule in a crude oil, is 2 nanometers long. It's bigger than some of the pore throat diameters, the pore throat radii. Okay. Human hair is 80,000 nanometers. Bacteria is 3,000 nanometers. Bacteria can't get in these rocks. Visible light can't get in these rocks, or the wavelength of light is 100 times too big to get through those pore radii. So if you were a C14 molecule, 2 meters tall, which is a tall guy around here, a conventional reservoir, you wouldn't even know there are walls there. Your doorway, you'd have to crawl to the move in there is a few miles wide. If you're in a Bakken shale, your pore throat doorway would be somewhere around the size of a pet door to a garage door. It's going to inhibit you moving. So it's phenomenal we're getting oil out of those systems. Okay, we're going to use 11 millimeter rods. Right here, we surround these with the fluid. We're not forcing it through the rock. We're letting the CO2 be in a bath, and we're doing that to minute fracture full that we think will dominate in fractured systems. Covered oil collected, analyzed by GC, and we get the recovery from it. Exposures at 15 to 200, 5,000 psi. We've done 105, we're actually done a lot more than 105 now of these 11 millimeter cores. References over here if you want details on mechanisms and results. Basically, with these 11 millimeter rods, all the Three Forks and Middle Bakken, you get essentially quantitative recovery with 24 hours exposure of CO2. The shales range from low 11% to 80%, these 11 millimeter rods. Rock geometry, of course, surface area is huge. We're dissolving stuff out of the rock. The CO2 has to get in. The oil has to dissolve and diffuse out. So surface area is a big factor. And this is one of the other sites we use. We make coins out of a rod, split it, make coins. So here we see the results of coins versus the rods. Higher surface area to volume ratio, the faster oil recovery, of course. 24-hour recoveries are greater than 99% from the Middle Bakken, and about 60% with the coins, here. And if we actually grind up the shale rocks, if we actually grind up the shale rocks to 1 to 3 millimeters, we get over 95% of the oil out, which implies these nanopores are accessible to CO2 for both oil recovery and storage if you could give me enough time and pressure to get the CO2 in there. Once again, to make fun of MMP, if you're on a conventional flood, conventional wisdom would say you don't have to go a lot of pressure over above MMP. But when we're extracting these rocks from these extremely tight samples, if we extract either shale down here, 11 millimeter rod, or the Middle Bakken 11 millimeter rod, going from 2,500 to 5,000, about MMP, doubling it, we double our extraction rate. If we go to 7,500, we get more off. Basically, what this says is that the hydrocarbon solubility is what's driving this out here. It's not a miscible type flood where it's physical effects. This is more of a dissolving type of thing in these tight fractured systems. And we also see this in pilot scale with CO2 injection. I don't think I want to spend the time on here. It's described in the literature. But yeah, we see the same effect in field surveys or field projects. Okay, so how fast can CO2 penetrate this rock? That's hard to understand, I'll tell you. So we've coated rods, these 11 millimeter rods with epoxy, and then sawed off the end so we get one end. So the only way CO2 gets in here and the only way oil gets out is through that one end right there. So we're assuming that CO2 oil production mimics, kind of mirrors what the CO2 penetration. And when we look at that, these are the molecular weight behavior. This is the first centimeter. We get all the molecular weights from C10 to C22 out pretty good. We look at the lower molecular weight here, the C10, you'll see that in the first centimeter to the second centimeter and the last 3 to 4 or 2 to 3 to 4 centimeters, we still get most of the C10 out, the fastest molecule, which implies we're penetrating in nearly 4 centimeters. The CO2 is in 24 hours. So we figure that the permeation rate of CO2 into these rocks is at least 3 or 4 centimeters in 24 hours. It's the only numbers we have so far. Finally, some isotherms. How much can you store? Basically, how absorptive are these things? This is with a ribothermite magnetic suspense imbalance, excuse me. This is 3 of the well locations. We have one more in there that commercial operator doesn't want to show. These are typical results. Here is the uptake from the Three Forks formation right here. Oops, pardon me. About 2 milligrams per gram. Same with the Bakken, middle Bakken formation, while the shales are up here at around 15, 14, 16 milligrams per gram. And the absorption curves in gray versus the desorption, again, they seem to be reflexive. You can put it in, you get it back out again. You have to maintain the pressure. Interesting that you only about 2,000 psi, you got about as much stored as you're going to get on this absorption mechanism. The Three Forks, again, very fair amount, but they're all with low TOC. I think primarily this is probably a clay thing, excuse me. We're looking into that. We don't have that data. The shales are very high, basically because, again, sorry about that. We're looking at high TOCs, middle buckets are low, again, probably clay. If we hand wave numbers here and look at, say, the lower Bakken as a shale, or lower Bakken shale as a storage thing, it's about 12 meters thick across the reservoir. We take our absorption values at 13, 14 milligrams per gram or 13 kilograms per kiln. We assume 50% of the rock is accessible, which may be well over mixed, over optimistic. I'm not a reservoir engineer. 1 square mile of shale could store half a megaton of CO2 or 2,000 square miles for a gigaton. So at least, I mean, again, this totally ignores engineering, but there seems to be a large capacity. So in summary, oil can be efficiently recovered from Bakken, Three Forks, middle Bakken shales with CO2, but you need high surface area and contact time. You also need pressure, and high pressure is better regardless of MMP. CO2 solubility is better at higher pressures regardless of MMP, and CO2 dissolves lighter hydrocarbons best, but improves at higher pressure. So pressure's good, unfortunately. MMP may have little meaning for tight fractured systems, I think because the mechanism of like flushing displacement of miscible flood is not what's going on here. We think it's probably more of a bathing solubility mechanism, and concentration gradient solubility diffusion likely controls oil recovery from rocks. We're looking into swelling too, and possibly viscosity. But right now, the solubility mechanism seems to explain the results. Potentially huge capacity for storage. I don't think that's great news or new news, but at least the isotherms tend to support that fairly well. And while showing the potential for combined EOR and CO2 storage in unconventionals like the Bakken, these lab studies totally ignore the engineering realities of field projects. That's where we're at. I'm not an engineer. Hopefully you engineers can use this and apply it. So thank you much for your attention, and that is the end of the video.